Thank you, and I'm in from New York, so I don't know if I get to say good morning still, or acknowledge that we're here at the end of a very long weekend. So adventures in not writing tests. So first, let me introduce myself as a father. I have a daughter, Lena. She's actually flown in this morning with her mom. Once we're done, I get to go spend a week in London with my family, but happy Father's Day to all the other fathers out here. Thank you for coming. Other than that, I usually introduce myself by Python version number, then I don't have to look at the year. When I started with Python, the book said, was an O'Reilly book, Learning Python, Python 2.2. Then up in the corner it said, newly updated for Python 2.3. But I had 2.4. I've worked with Plone, I've worked with Twisted, I've worked in the financial industry. I did a little bit with virtual worlds and video games. I've been at Bloomberg since 2017. And in 2019, I switched over into one of our system reliability engineering teams. And in 2020, I switched into our data services department, where I work on our data gateway. This sits in the middle of many of the Bloomberg workflows. We're a gateway. So the code calling us, we don't own. The code we call, we don't own. Some of the code in our own executables, we don't own. But we do have billions of requests per day, and we do want those to all work. And they are going off millions of semi-independent code paths. I say semi just because I'm optimistic. They might cross. So a lot of what I do really comes to ingest and process telemetry data. In a sense, I am grabbing data science tools all the time. So show of hands, who only read the title and decided to come to this talk? Okay, you will have a slightly different experience from those that read the title and the description. This is a talk about how to not write tests, or at least how to reduce the time we take to do it. We will still have tests, but we're going to get some help writing them. And no, I'm not just taking a large language model and telling it to write tests. That's interesting. I'll go see your talk. So I'm going to focus a lot on what I call analysis code. This is code that starts with a question. So what does my latency look like? What services do we rely on? Is there anything interesting in this data? We initially don't know the answer. We initially think we're only going to run this code once, because once we have the answer, that there's nothing interesting in that data, we'll move along. And at that point, you might make a fairly reasonable decision that you're not going to write tests because you don't know what you're doing, you don't know what the right answer is, you don't know what to test. But quite often, we do find something, and we present it to someone, and they look at it and they go, that's great. Can you run it again on today's data? Can you run it again on tomorrow's data? Well, I mean, tomorrow, I'm not expecting a time machine. Can you run it on this other data set? And now that means we should add tests because we are running it over and over again and it's approaching production. It doesn't mean we know what data it's going to be fed. That part is still true. We don't know the future. So I'm going to use a motivating example through this just to explain what's behind the examples. I'm imagining a system that looks at 10,000 samples of incoming requests. And the questions that kicked off the analysis are, how would our system perform at various capacities? Oh, and don't forget, some clients are batch and some are, I've labeled them timely. There's some kind of interactive thing. The batch clients, they can wait. They can roll over to the next minute, it's fine. But we'd like to know how long the system is fully utilized. Now, how long would the system have been fully utilized if we had less capacity or more capacity? Those are the sorts of things we're going to look at. But the star of what's going to save us some effort and get some better results is a Python library called Hypothesis. Hypothesis, taken right from their website, is a Python library for creating unit tests that are simpler to write and more powerful when run. Finding edge cases in your code you wouldn't have thought to look for. It's stable, powerful, and easy to add to an existing test suite. It works by letting you write tests that assert something should be true for every case, not just the ones you happen to think of. Remember, we don't know the future. We don't know what data is coming to us. So if we think of a normal unit test as set up, perform some operations, and then have some assertions, Hypothesis changes the first step. Instead of setting up, we define what the input data looks like, and then we hand it all over to Hypothesis to get data that looks like that and run it through the tests. This is called property-based testing. Haskell has a quick check library, if you've heard of it. The thing is that Hypothesis is almost pathological. It will come up with the cases that you never wanted to see and feed those through along with it. And we'll see that come up again and again. So how does this help? Well, we're now relieved of actually creating test data, which is good because we didn't know what to create. Instead, we can just describe the data that would possibly be valid, and Hypothesis will take care of it from there. So if we say, Hypothesis, I have a floating point number. A Hypothesis, give me a floating point number, 1.797 times 10 to the 308. This is a floating point number. It's larger than the ones I normally think of, but there's nothing wrong with it. And if I said I was going to work with floating point numbers, that ought to work. Give me another one. Negative 1.192 times 10 to the negative 7th. Okay, that's a little smaller than the ones I normally think of, and it's negative, but yes, it ought to work. Let's try another. Oh yeah, that's also a floating point number. And I never remembered to handle that one. So this is the sort of thing that Hypothesis will do, not just for floating point numbers, but also for text or anything else. But we're still writing tests. Let's stop that. Hypothesis has a tool called ghostwriter. It installs it when you install the library as a command line tool, Hypothesis write. And we can tell Hypothesis to write some tests for sorted, and this is what Hypothesis gives us. In order to test the Python standard library sorted function, it takes an iterable, it takes a key, and it takes reverse. And it runs. And the type hinting on that says that we're going to have integers and text. And this will just feed the key as none. If someone has a good strategy for generating callables, all possible callables, I think we have advances in computer science that we can use that for. Now, important to note, there's no assertions here. The assertion is that you can feed it anything and it doesn't crash. Let's take some more examples. If I try to test ceiling, it tells me that the input is nothing. That's what happens when there's not enough type hinting. So we're going to have to fix that. Ceiling ought to take floating point numbers, and we can go ahead and write an assertion. My assertion is that if you feed a floating point number to the ceiling function, you should get a number that's equal or greater. How many people see the flaw in that right off the top? We got 1, 2? Okay. Don't worry, it's on the slide. Hypothesis found 2 flaws. I assume each of you had one of these. If you feed not a number to ceiling, you get a value error. If you feed infinity to ceiling, infinity is also a floating point number. Infinity cannot be converted to an integer, and you get an overflow error. So the completed test here would be have floats, don't use not a number, don't allow infinity. It should follow this behavior. And then a separate test, if you give it not a number, then we expect a value error. If you give it infinity, we expect an overflow error. That's a complete test for ceiling. Oh, I saw cameras up. Just showing another example, group by will give us also some iterables and a key. But we haven't done anything with our code, and the standard library has some tests already. So this code is from that fictional system, find max available loaded. It's probably a particularly horrific way of finding the length of the longest consecutive sequence of trues or falses. But it's got some good errors in it. So it goes ahead, it groups it, it sorts it, it takes the max sequence of false and the max sequence of true and returns that as the maximum time available and maximum time loaded. And when I tell hypothesis to create a test for this, it goes, oh, here's all the possible iterables of Booleans, and I'll just pick those as I go. Okay, which I would not have remembered that I could feed it a set and that's iterable. And then it writes me the test here, and that can run, and if I run it, I get a key error. Because if you feed this the empty sequence, which hypothesis tried for me, there's no false, there's no true, and it does not work. So we'll have to make a small change for that. We'll take the maxes of false and the maxes of true, but we'll default to 0. If there were none in there, then the time that it was loaded is 0. But we use data frames an awful lot around these parts, and well, we probably should work on that. If we type hint this enrich usage function, which we'll see in a couple slides, but it adds some columns. I've written this I don't know how many times. It takes a data frame in, it returns a data frame, and it's got a list of some other stuff. And hypothesis will write this test for us. And when we run it, it will tell us that we didn't account for the empty data frame case when there were clients. So in this case, it's got a client that's an empty string, but an empty string is still a string. And it's saying it cannot index the empty data frame by a string of any sort, which makes sense because we kind of just naively wrote the batch clients is the sum of the batch clients in the data frame. Okay. But let's take a look at what sort of data we get from this data frame. Example, empty data frame. Okay, we knew that. Let's try another one. Oh, I get the feeling this is always going to do this. I could just write a test for empty data frame. So fine, we'll make our own data frame with columns and data. So we can do that. Let's get a list of client names. Let's get a list of usage values. That'll just be a bunch of floats. We'll work with it. Let's get a list of whether they're batch or not. Okay, we'll take a list of batch clients, we'll zip it together, we'll make the list of batch clients, we'll take the number of clients, we'll go through a data frame, and we'll pull off every next one, just going down the list and segmenting it out so they all wind up fairly randomly assorted, and then we can test it. And this will give us a data frame, and it will look like this, or something like it. It's random, it'll be a little different each time. But that's not bad. We've got some infinities, we've got some nada numbers, we've got some kanji. I'm sure we accounted for all of that. And we can add some asserts again. So we're going to assert that the sum of the total column is equal to the sum of the other two columns. And we're going to assert that on each line, that the highest in each column behaves in a reasonable way. Fine. We can run this, and not surprisingly, because it wouldn't make a very good presentation if it didn't come up with an error. We get an error. It turns out if you feed it infinity and negative infinity, you get a not a number when you start doing math on infinities. A not a number plus 0 is not equal to a not a number without 0 having been added, because not a number is not equal to not a number. It's also not greater than or equal to not a number, which you can get from a different code path. I'm probably preaching to the choir here, but not a numbers are really troublesome. Okay, so infinity is a problem. We'll stop allowing infinity. Infinite usage probably doesn't make any sense. And for the other not a number case, it actually comes into accessing a client that isn't in the data frame. So we can just say the total of the batch clients is the total of the batch clients that actually have data. So there we have it. And that will actually point out another problem, which is that if you have a negative number in there, your total can be negative and an individual column can be not negative, and we were not covering that, but negative usage doesn't make sense in this case. And now we've documented that we can take usage values, they cannot be infinite, and they have to be positive. And in a sense, what we've done is we've documented what this function takes, what cases this function will not handle, and which cases it will. So as long as the client names are unique, we can do this. But we're not going to keep doing this. This is an awful lot of work, and I think at least some of you expected to save work here. Hypothesis extras pandas will let us create data frames. This is an example of how it creates a data frame. Pandas data frames, you give it a list of columns and what the types are. So here we've got a total column that's a float, and we've got a percentile column, which percentiles go from 0 to 1. So let's go ahead and put that in right from the beginning. And now we can run a test on estimate needed capacity, which just takes a percentile, really. We'll see it in a couple slides. Well, this will still produce an empty data frame. So this is an empty data frame with a total column, which will create a not a number. And then it gets fed into the ceiling. Ceiling doesn't take not a number. We covered that. However, if the data frame is empty and we're estimating the needed capacity, we know we don't need any capacity. So we'll go ahead and change our code to say If you give me an empty data frame and ask how much capacity do you need, we know the answer. It's 0. And now we would pass. There are some more tools. I'm going to cover one of them. Assume covers the case where hypothesis generates data that doesn't make sense to test. You can get some distance with many other tools, but setting maxes and mins and things. But sometimes the data as generated just doesn't make sense. And if we run assume and we calculate something that's a false, then we'll skip that. So in this case, we're going to make the assumption that we're not interested in testing the case where we have much more capacity than we need. If the analysis code does not work in ridiculous amounts of capacity, we do not wish to test that. So in this case, we're assuming that the capacity number that we're feeding to this, again, fictional function, is not more than 10% larger than the greatest number in the whole rest of the data frame. The highest usage anywhere in the system that's being tested, we don't have more than 10% than that. So assume we'll just skip those. A few hypothesis tools that I want to mention, but I did not find time for in this presentation. Target lets us say this makes a good test. And the way that works is you feed it any value that, again, that you can calculate that will increase when a test gets better in some way. And it will walk down that path and try to optimize target as well as testing other things. Example says specifically test this. And you can say, test this every time, these specific values, and it'll also work a little bit around that. Register type strategy lets you say, for this particular type, this is how to generate data for it. And in fact, if you want to see how that works, I have to put new material into this presentation and give it at EuroPython next month. I'm going to take the data frame out and put that in. But essentially, you match a function and you say this function will generate data for this type, and here's how to create it. There's also settings. There's settings to control timing. A very common error you'll encounter is that hypothesis feels like it spent too much time trying to generate tests for a particular case. You can go ahead and narrow that down, but most of the time I find myself just reading the message that comes up that says change this setting with a decorator, and going ahead and saying, yeah, I'll spend a second on this, it's okay. There's also randomization settings. Again, I tend to be pretty fine with it, but some people don't like their CI to fail unexpectedly because hypothesis just tested something different. And now the CI just failed and somebody should do something about that. I'm content the CI is there to tell me something. And when it fails, it will give you a decorator to reproduce it. So you can just copy that out of the error, and it all works. But a fairly good portion of people don't like that habit, so that you can tell the CI to test the same thing every time. And just run the more randomized tests on the developer desktop, where what it'll do is it creates a hidden folder, and if you ever fail something, it'll test that every time. But when you pass, it rotates a little bit into different selections. Okay, so conclusions. First of all, do write tests. And do use test-driven development. Do write tests first where appropriate. Where is that appropriate? Go find another talk. I'm more willing to acknowledge that sometimes it happens that we have the code and not the test, and then we need to do something. Do use hypothesis rather than or in addition to selected examples. If you're going through the process of saying, oh, well, this is the production data from October 28, and every time we run on the October 28th production data, that's our test. Hypothesis gives you a way to cover things that did not happen on October 28th, other than picking up May 14th and having two of them. This is, of course, because you don't know what data you might get. So hypothesis lets us describe all the valid data, and then we can test with that. So I will take questions. I also have hypothesis stickers. These, I guess I have 100 of these, so don't be shy. Zach Hatfield Dodds, who's the maintainer of Hypothesis, saw me at PyCon and went, oh yeah, well, take some stickers. I got lots of them. Now I have lots of them. Thank you.